Hello everyone, I'm Akshata Jha from IIIT Hyderabad. I was an OpenDaylight intern for the summer. So I worked on a project on creating the Debian package for OpenDaylight. My mentors were Daniel Farrell and Stephen Kitt. So I'll move on to how I worked on, what I did in this project. So why do we need Debian packages? So for OpenDaylight, RPMs already exist. Now, this is the pipeline that an RPM follows. So RPMs are consumed by Puppet and Ansible, which is then consumed by Packer, like Vagrant base boxes and Docker containers. So there's no such pipeline, because there was no .debs, there's no such pipeline that existed. Puppet OpenDaylight used a tarball for Ubuntu-like OSs. So if we have debs, it will follow a similar pipeline, and it will be easier to maintain, and also ODL upstream will provide installation options. So it's always better to have it in the upstream. Now, the Debian package that I built is a very simplified packaging format. It is reproducible and automated. It provides service manager support like systemd and upstart. Also, it makes use of Jinja2 and YAML templates. So it's basically dynamic. We can build .debs for any of the OpenDaylight versions that are available. I can just show you what the vars file looks like. Yeah. So this is the vars file, YAML file. So here we have the version, major version, the minor version, the patch version. So these are the variables that are used, that can be used to build a dynamic .deb package. And this .deb package handles all the dependencies. So say for Boron, the dependency is Java 8. It will be automatically included in that. For Beryllium is Java 7. It will again be included in it. So we don't need to install Java 8 and Java 7 separately. This is the GitHub repo where the code is being hosted. It's in OpenDaylight integration packaging. There's a dev folder where we can find the code. Now, this is the directory structure of the entire Debian packaging. So we have a build.py script that uses cache.py and build Debian files.py. Now, cache.py uses YAML templates and decides if all the artifacts that are needed for the OpenDaylight are present or not to build the .deb package. If not, it basically downloads the .tar.gz file. If it's already present, it will just ignore. And build Debian files.py will build all the files that are needed for Debian packaging, making use of the templates again. So here we see that we have templates, changelog template, the control template, and the rules template, and all the other files. These files are made use of by build, build Debian files.py makes use of these files. And I showed you the YAML file, which is all the variables defined in it. Now to build a .deb package, this is a command that we run. We execute the script build.py with the arguments. This is the major version. This is for the Boron release. The minor version, the patch version, and the .deb version that we want. Now, since I already had the .tar.gz file downloaded, it says already cached. This is what cache.py does. Then again, I haven't included the entire screenshot, but yeah. So finally, in the end, we see that .deb is being built. Now, after the build, there'll be a specialized directory called OpenDaylight, which again contains specialized directory for the particular OpenDaylight version. So we have, say, a .deb for Boron release, that is 5001. So these are the this is the directory structure inside OpenDaylight. And inside the specialized directory, again, we have the Debian directory, which basically contains these files. So these files have been generated using the templates that I showed earlier. So it will be different for different releases of OpenDaylight. Now, once the .deb has been built. We'll now install OpenDaylight. Now, how do we do that? We'll use, if we built it in our local machine, we can use sudo gdebi to install OpenDaylight along with all its dependencies. And here we see that it's being installed. Also, if we don't want to build it locally, it's been hosted on the OpenSUSE website, build services. So for Debian 8.0, we can just add the repository and install it, apt-get install. And similarly for Ubuntu, we can do the same for different versions of Ubuntu. Now OpenDaylight comes with systemd integration. So systemd integration basically helps people to not actually touch the binaries in the bin folder. So we can just start OpenDaylight using systemctl start ODL, and when we see the status of OpenDaylight, we see that it's active and it's running using just systemd. And we can then SSH into the Kref shell and then run commands on the Kref shell. Now once this is done, if you want to just stop OpenDaylight, you can again use systemd to just stop. You can check whether OpenDaylight is active or not. It says it's active. Now I stop OpenDaylight and then I see that the status is dead, inactive, right? So again, a Debian package we build, we install. Now how do we remove? So sudo apt-get remove will remove all the folders, all the files, OpenDaylight files. And sudo apt-get purge will remove all the configuration files as well. So yeah, I think all of us do this very often. Now the benefits of having a .deb package is that OPNFV installers that support Ubuntu-like OSs can use this, can use the upstream tools that are available. So .deb is available upstream. And also it will be easier to maintain. And the future work of this project, so I've just currently built the .deb project, .deb files. Like I haven't integrated it yet into Puppet and Ansible. That's what I'll be working on next. And then also provide examples in Vagrant OpenDaylight. And yeah, and then make OpenDaylight .deb available in an official repository. So I think that was my work. Thank you.
Good. All right, sorry about that. So everybody, so my name is Ching Wong from Clemson University, and my project advisor is Annual from Brocade. And my topic today is REST request load balancer for OpenStack and 3-node OpenDaylight cluster deployment. So here is the agenda. So first I will do a quick overview for OpenStack and OpenDaylight. And I will talking about OpenDaylight clustering and the problems. So, and that will introducing the solution framework, which includes a REST request emulator, load balancer, and 3 OpenDaylight clustering nodes. And then I will talking about the emulator design. And then I will talk about the load balancer emulation and summary. And then I will talking about the deployment and load testing. And at the very last, I will give the results and conclusion. So the background for basically is OpenStack will working in the front end, and OpenDaylight will working on the back end. And OpenDaylight is actually expose the northbound REST API to handle the network complexity that moves from the neutron services. And then OpenStack just simply send a REST request to the OpenDaylight. That's a big picture. So, and then we need, then we're talking about OpenDaylight clustering. So one might argue, so okay, so why we need OpenDaylight clustering? Is that one single OpenDaylight server node is enough? The answer is no, because if we considering the scaling, the high availability, and data persistence, we do need OpenDaylight clustering. But what is the problem if we do that? So the question then would be, which backend controller node should the OpenStack then talking to, because you have multiple cluster nodes, right? So to be more specific, then that will be what backend metrics that need to be considered. So we think there are a couple metrics, which is like the current workload, the connectivity status, and the service status, and some deep health status. I will explain more like in a couple minutes. So we think the one possible solution is we need an entity between the OpenStack and OpenDaylight. And that entity should be able to route requests from OpenStack to the different OpenDaylight cluster nodes with different weights. And it's able to perform some like node up and down check, and it's also need to perform some deep health check using the OpenDaylight health monitor module. That is also the REST API exposed through the northbound. Also, that entity requires the good performance to handling the REST request, of course. So here is our solution framework. It basically has 3 components. One is the REST request emulator that simulates the REST requests from the neutron services to the OpenDaylight. And we have 3 OpenDaylight nodes just to simulate that clustering mode. And we have a load balancer in between. Okay. And we deploy this really into all-in-one virtual machine with almost 5 gigabits memory. And we will have 3 OpenDaylight cluster running, like each one running in a Docker container. And load balancer will run it into a load container as well, a Docker container as well. So then we need to design a REST request emulator. Okay, so the goal here is we want to design such a lightweight test framework. So because so OpenStack is be able to send REST requests to the OpenDaylight, of course. But why we don't use that? Because that framework is too heavy. Okay, so people might even like wait for 10 seconds to wait for network status to display. So it's time consuming. So we want to have a light test framework to help us to speed up. So that leads to a couple features for the emulator. So one is we want that, as I said before. So then we want the test the OpenDaylight cluster independent of OpenStack. So we don't need OpenStack anymore. We just need the emulator to generate the REST request to the OpenDaylight. And then we need some like mock object to simulate requests from the neutron. So for example, if we want to simulate creating networks, if we want to simulate creating subnets, if we want to create ports. So each that network operation has different like object to send. So we want to simulate that object as the input for the simulator. And then we will perform some heavy load testing to generate traffic to the OpenDaylight cluster. And we think some client context may be useful for some deeper performance testing. So when I say client context, what I mean is we want to simulate, okay, there is a client trying to to create a network, and you got the network UUID. And based on that UUID, you can create multiple subnets. So maybe on one subnet, you have a UUID, and you can create different ports. So we want to build up such like hierarchy architecture for this emulator too, to try to better simulate the OpenStack behavior. Okay. So, and then for the load balancer, so the question is, what load balancer is most fits into this framework? So it turns out we need to evaluate multiple open source load balancers. So is there layer 4, or are they layer 7, or are they both support layer 4 and layer 7? Like, is that active health check, meaning they can sending the REST request to the backend and analyze the response, like body or header, right? Or it's just passive. And how many load balancing algorithm it supports. And some other features like how many protocols it supports, is that a high availability for the load balancer itself, and SSL offloading, things like that. So I want to, because we have like every detail for the metrics in Excel form, but here, because of limited page, I just want to give a brief summary for the load balancers we evaluated. So we evaluated HA proxy, the Ninjax, the Pound load balancer, the Zen load balancer, and the LVS load balancer. Okay, so as you can see, maybe like the first row is they support layer 4 and layer 7. So it turns out, for example, LVS only support layer 4. So that's probably not a good load balancer because we really need layer 7 rerouting thing, right? So HA proxy support layer 4 and layer 7. Ninjax support layer 7. So all rows are support, so that's very good. And regarding to, in terms of the routing algorithms, so turns out Pounds has only 5 algorithms supported. HA proxy, Ninjax, and other load balancers, they have around 10 load algorithms to support, which is good. And for Pound, for the health check, Pound are not supported deep health check at all. So which probably not good balancer again. So HA proxy support active send the deep health check and the request and analyze the response. Ninjax is be able to send the request and analyze response, but it needs you to pay for the commercial version. There are some other metrics like they support HTTP, HTTPS, and IPv4, IPv6, things like that. And then we have some load testing results. So basically, we generate heavy traffic for each pieces of the framework. So we generate heavy traffic for OpenDaylight node to the load balancer and to the load balancer connecting to the OpenDaylight. So again, I pick up some results here. So first test case will be we have 20,000 requests with one concurrency number. And then the second one will be 3,000 requests with 100 concurrency number. And the third is 3,000 requests with 300 concurrency number. So if you look at the table here, you can see pretty much those 3 load balancers are their performance in terms of REST request number per second. They almost like fall into the same range. There's not a significant difference between like one to each other. So we think, okay, so from that angle perspective, they're about the same. Okay, so then we have some conclusion here is HA proxy probably will be the most fit open source load balancer for our framework. The reason is because first, it supports both layer 4 and layer 7. And the second is it supports both health check and deep health check. You can actively send the health check, and it can analyze both response header and the body. And it has rich load balancing algorithms. It has a high performance in terms of requests per second, and it has a least field requests in average. So Ninjax is potentially an alternative one, but it just needs to pay for the commercial version to the health check features. And both HA proxy and Ninjax supports multi-instance features, so potentially that means you can have, it supports the high availability for the load balancer itself. I guess, so here is the link. So as I said, I have a lot more detail about the metrics and the testing data in the Google Excel form. And here is a GitHub for the emulator I wrote and some slides reference. And acknowledgements, I just want to say special thanks for my mentor, Annual. I can't finish this project without his great help. Thank you, Annual. That's it.
Hello, everyone. My name is Kian Ha, and I'm a core reviewer on the Jenkins Job Builder project. So what is Jenkins? Jenkins is a continuous integration server that helps improve your productivity by building and testing your software projects. Jenkins Job Builder, on the other hand, takes in simple descriptions of Jenkins jobs and uses it to configure Jenkins. It is easy to use, and after this talk, I hope I can impart you with knowledge on where to get started with JJB and what JJB can do for you. So creating a job in Jenkins Job Builder is very simple. You can create a job by, as shown, where you write just -job and the name of the job that you want below it. This isn't particularly useful as it's currently doing nothing, but we can make it do something, such as publishing from a plugin. So using the robot plugin as my example, we can collect test results and publish them to the robot framework. In the following configuration, I called my job robot job, and I configure a couple of options in the robot plugin. In particular, output path and other files. So I'm just showing you here that I created the robot job. And inside this robot job, I've set a couple of options, but seemingly more other options too. So some plugins have a lot of different options that you can set. And what Jenkins Job Builder will do is it will set the default option or default value to the options if nothing is passed to it. To override these default values, simply add in the option's name and set it to whatever you need it to be. So if you're defining multiple jobs that differ slightly between one job over the other, maybe one job has a slightly different name over one another, or another job does an extra thing, you can create a job template. For instance, you can create a job template that differs in name using the curly braces. And this will differ. For instance, you can create a job template that differs in the name using the curly braces to indicate that name is a variable. So in this example, I've created two job templates, one job called the robot job 1 and the other robot job 2. They differ in name. They not only differ in name, but if you take notice, the robot job 2 also prints out to the shell hello world. Along with creating a job template, you will need to create a project to use the job template. A project collects related jobs and provide the values to the variables in the job template that was made. Many jobs can be defined using macros. A macro lets the user to easily call a frequently repeated task. This is useful as it is cleaner than repeatedly rewriting the same code for the same task. So for example, we can set up a macro, as you see in the first block of code, for the robot configuration that we have made in the previous job configuration, and call the macro for the two job templates instead. As you can imagine, this will help you keep the code really simple and small if you have a lot of jobs in the future. Just a quick summary for the TLDR. Keep related jobs organized in projects. Job templates help simplify similar jobs, and macros are great for frequently repeated tasks. If you're interested in the Jenkins Job Builder, I provided the link, or you can do a quick Google search. Jenkins Job Builder, it should be the first link. And that's my presentation. Thank you for listening.
Yeah. Hey everyone. Yeah. Hey everyone. I'm Kumar. So my project was JVM monitoring framework for OpenDaylight, and my mentor was Luis Gomez. So what's JVM monitoring framework first of all? So one-liner, it's a collection of general purpose resources for harvesting and analyzing various matrices generated by ODL controller. Now, what kind of matrices can be generated by ODL controller? Basically, it can be any sort of object generated by either JMX server or something like a perf matrix. So the matrices that are currently supported are just the JMX MBs, and that too a limited set of it. I'll come to that later. Now, once we have the framework, then we can leverage it to write long duration / short duration feature agnostic test for the CI infrastructure that we have. So we have very small set of tests right now, but say a test could be something like is some sort of SLA that is getting honored during the course of time, say for 24 hours during which the ODL controller is running. Say something like if the garbage collector takes at any point of time more than 1 minute to complete, that's kind of a long time for any Java application. So something like that. The major components include decanter, a sort of data store in which we dump all the data, a general purpose library that we developed, and a small canonical test of robot test suite that we use to test it, and obviously the script to configure and glue it all together. We also have support for plotting / analyzing the matrices that we generate, matrices that we harvest. Also, we have support for getting the real-time data from the MBean server. The major components, as I already said, decanter, data. Now, why do we use Elasticsearch data store? Short answer is because that is supported, that is the one that is supported completely by the decanter community. But it could be any other NoSQL solution because we have the objects which we need to dump into some sort of data store. But one plus point of Elasticsearch index, Elasticsearch reverse index is because it supports a very rich set of queries, which is generally not supported by other NoSQL solutions. But we do have Cassandra that is being developed actively by the decanter community. Then the configuration script for the entire decanter / Elasticsearch stack, and the general purpose robot / Python library. So this is the high level view of what we tried to achieve. So if you can see, we have a cluster of controllers at the bottom, which each of them has an agent of decanter plus configuration script running, which configure it to work as per our requirements. So we developed some template configuration scripts which we can use as per the use case that we have. So say if you have a short duration test that is going to run, say a 40 minutes duration test, we have the scripts that can configure the ODL controller plus the data store as per the requirement, which you can inherit in the script plan. We'll come to that later. And then we dump everything that we get into the data store. Above that, we have the Python keyword libraries. Now, this has two interfaces. One is the data store facing interface and one is the user facing interface. So the data store interface, you can ask questions like, okay, start the data collection into the data store or stop the data collection in the data store. Then we have the user facing interface of it, whereby user can ask it, user in this case will be the robot keyword library. That can ask, okay, aggregate the entire history that we collected from the start of the epoch, that is the booting of the ODL controller. And then on the top of that, we developed a small set of robot keyword libraries that can be inherited into the existing robot test we have in the integration test repository. So you can just into the start suite or tier suite of any test that you have in integration test, you can just add a line like plot the data till now. So it will plot the entire data that is have for say a thread matrix right now. We also have support for real-time data fetching, so we can ask what was the latest thread count that we had, or what was the latest garbage collector time that it took for the entire garbage collection. And then we go on to, then we have support for generating the plots. So basically it leverages some Python plotting libraries to develop the plots that we generate from the data that we store. So the major components, so once we have the carafe decanter, so short introduction, it's a monitoring solution maintained by the Apache Carafe community. It's used for collecting / appending / scheduling the JMX MB in matrices. It has a support for rich set of regexes, so I can ask something, very simple question. Actually, it's not that simple if you go to Pythonic regexes. So you can ask something like the object name should be java.lang, whereby the type is something and then the subtype is something else. Now, in our case, we use it to collect some very basic matrices like the class uses, or the thread count, or the memory object, or the heap uses. Actually, it's not that small. So, yeah, currently we have a pretty decent list of objects that we support. So we have support for heap memory uses, or the non-heap memory uses, or in the garbage collector we have the garbage collector thread, the thread count for the garbage collector. So actually, so interesting story is someone used the framework and then they contacted us that the total number of thread counts in ODL controller, the out-of-box ODL controller in in the Jenkins CI server used to go above 400. So we couldn't do anything about it, but probably down the line someone will probably use it to mitigate the problems that they have. Then there is Elasticsearch Index. So if you have used Elasticsearch Index, if you have used the queries in Elasticsearch Index to be exact, those are like really complex, and just to say it's horrible to write all those queries. So we use an object relation map, an ORM wrapper over it to make the queries simple for everyone. And say if you want to add your own new data store, you just inherit from the data store class that we have in the Python library, and just overwrite all those APIs that are there in the Elasticsearch Index, and then it should probably work out of box for other data stores too. And obviously it works very well in multiple controller environment. So basically it multicast in the entire LANs, in the entire subnet that it has, and joins every Elasticsearch Index that it has. So we don't need to provide anything offline or hard code. It just discovers the entire topology online. So that's a pretty good plus for Elasticsearch. So the Python robot keyword library that we wrote has two interfaces, the user facing and a data store facing interface. So data store facing interface interacts with Elasticsearch to retrieve / search for the objects that are dumped into the Elasticsearch Index. So there are three kinds of queries that we support currently. First is the range query. So we can ask something like, okay, get me all the heap memory uses for last 200 minutes. Or we have the partial queries or the point queries. So for the point queries, we can have something like asking for the real-time data fetching, that is, get me the latest thread count, or something similar to that. After that, we obviously leverage the Elasticsearch interface and DSL query wrapper to augment our search. And we have the user-facing interface that allows robot test suites to interact with the Elasticsearch installation. So it allows the user to ask the framework question like, okay, let's start the data collection. At some point of time later, we stop the data collection, and then we can perhaps generate the plot of it. And I covered the robot test library. So some plots that we generated, I can't show because So right now in the Jenkins gate, we have something around 50 tests that run this JVM monitoring framework. That's less than 2% of the total tests we have in the Jenkins framework. But still, we are trying to increase the count. And if you want to integrate, and if you come across any problems, you can always contact me. So these are some 24 hours plots that we generated. So basically, if you see during I'm not sure what happened during this time, but basically during this time, when you can see the spike, it might mean that there was some test running which spiked, which increased the CPU load a lot, and then it became constant. So probably someone can use it later. We also, I can also show some plot in the gates that we have. Yeah, so these are the 3 nodes cluster that we in which we added the plot. So basically, it plots everything and then sends it to the logging servers. So let's see. So these are, by the way, these are very short duration tests. But you can always write the 24-hour test later. So these are the kinds of plots that we generated out of it. And if you see that that Karaf thread after and before, basically someone added it later because he saw in the plots that the number of threads that were getting spawned was a lot more than the required. Yeah, so yeah, that's pretty much it. Yeah.